2014, in celebration of von Nau's Nobel Prize, has been declared the International Year for Crystallography. At the same time, the Brags are working on determining the structure of sodium chloride. These remarkable scientists were some of the first of up to 28 Nobel laureates in this field over the last century, from the discovery of the famous double helix of DNA to wave particle duality and others given in the field of chemistry. Even the Curiosity rover is taking X-ray diffractions of the soil on Mars. What would a robot do with all that money? Crystallography, concerned with the structure and properties of crystals, examines the spatial arrangement and symmetry patterns of atoms in condensed matter, thus investigating the properties of different materials. Scientists have discussed the definition for as long as they have been examined, constantly changing. Previously, crystals had order and periodicity, meaning that a unique cell could be repeated and stacked over to form a lattice with a set of primitive vectors. For simplicity, Miller indices are used as a notation system for these vectors and their planes. Since Shackman's recent discovery of quasicrystals, it has been seen that a crystal may have order without periodicity, and to have strange symmetries previously prohibited, namely five-fold rotational symmetry associated with pentagonal lattices. So how do we know if it is ordered? A diffraction experiment, like the one Young did with two slits, must be carried out using waves of amplitude similar to the slits. Thus, a crystal acts as a 3D diffraction grid. The patterns achieved give so-named Bragg peaks, which help us to find the spacing of the planes using the equation developed by Bragg Jr., squaring the signs for substitution of D and comparing with a mathematical model. Back then, structures could take months to find. Nowadays, with powerful computers, several crystals can be analyzed before coffee. There are three main types of X-ray crystallography. The most common is the powder diffraction method, due to the fact that most crystals are not single but polycrystalline. To overcome this issue, crystallographers grow their own crystals. But why use X-rays? They have a wavelength of the order of a few angstroms. They are scattered by electrons, and so Bragg peaks resemble delta functions giving Fourier transforms of the electron densities inside the material, so we can determine the composition. X-rays are not ideal for similar atomic number elements, thus we need other waves with smaller wavelengths with these typical energies. So, X-ray and neutron scattering are used to complement each other. Also, scanning tunneling microscopes and atomic force microscopes can be used to digitalize real-time images of the material set. We are constantly searching for new semiconductors, superconductors, lasers, and many other materials. To investigate these and their properties requires the availability of large crystals of good quality, which constitute some of the most important tasks of crystallographers today. Paul Canfield explains that growth is like fishing. The good fisherman will know where to look for fish, and so a good crystallographer will know what kind of elements to combine when searching for a new material, knowing which field he wants to investigate. Several types of growth are known, such as vapor growth or solid-state growth. There are also others used in industry today, such as the melt growth pulling up, where a molten metal is pulled up from a rotating seed, producing a large ingot of the material. However, these methods are not all good, as they do not give single-phase compounds, so I shall focus on Canfield's method of flux solution growth. In my experiment, I produced crystals of nickel-bismuth-3, found to have coexistence of magnetism in the superconducting phase by researchers in the Universidad Autónoma in Madrid. Its coexistence was found to be caused by amorphous nickel impurities. I want to try and increase this magnetic phase by doping the superconductor with ferromagnetic elements iron, manganese, and cobalt. To grow a crystal of interest, you must find phase diagrams for the constituents. These diagrams show how two elements combine in different ways to form different compounds. We see they have three distinct regions: eutectic points, minima and liquid regions; peritectic points, where there are mixed liquid and solid phases; and congruent regions, where a homogeneous liquid turns into a homogeneous solid. From these diagrams, we can choose an initial composition for the mix. Bismuth is a good flux metal as it solidifies at a low temperature relative to the nickel. It is important to choose an optimal temperature for profile. This should give maximum time for crystal growth to avoid multiple nucleations. However, other important periods must be determined, initially to allow for homogeneity of the liquid, at the end to allow time to pull the crystals out. So, as our crystal forms, the bismuth flux increases. This excess can be then decanted using a centrifuge. We must make sure to close the materials in a good environment. The crucibles we use to hold the materials in are made out of alumina, which softens at 1200 degrees, well above the highest temperature reached. Another crucible filled with glass wool is placed above the first to catch the excess flux when we decant it. These must be made as inert as possible, so we place them in quartz ampoules, tubes, which are then necked and vacuumed and back pumped with an inert gas before sealing off. Now they are ready to be put in the oven and wait. When we pull them out, the transition must be as quick as possible so that the bismuth does not solidify on our crystal. Luckily, we allowed for a 50-degree margin. Spinning does not take very long, so now we have the crystals, we can prepare to X-ray them.